and welcome back to the CCNA journey with me, Ryan. And in this section, we're going to look at Unicast and Multicast and Broadcast and understand what they actually mean. And then I've also popped in a section around CSMA CD, broadcast domains, and collision domains. Now it's worth noting that broadcast domains, collision domains, and CSMA CD is not formally listed on the blueprint, but they're important to understand as a prerequisite to the CCNA. And Unicast, Multicast, and Broadcast are used throughout the CCNA. So if you do not understand Multicast or you don't understand Broadcast, then protocols like OSPF and DHCP will be a bit more tricky. So this is a optional video that covers kind of prerequisite knowledge that you need to learn in order to understand later topics in the CCNA. If you understand Unicast, Multicast, and Broadcast, and of course the broadcast domains and collision domains, then feel free to skip the video. If not, or even so, if you do know it, it might be worth just sticking around and having this as a refresher. For those who don't know, you can contact me here on YouTube, LinkedIn, Twitter, and Facebook. And don't forget, if this video is useful, please do like and subscribe. Discussion around Unicast, Multicast, and Broadcast. Now, Unicast, Multicast, and Broadcast happens at both layer 2 and at layer 3. Remember, layer 2 is the data link layer. And this is where devices like switches live. And layer 3 is the network layer. And this is where devices like routers live. Now, switches, they actually, or layer 2 I should say, use MAC address for communication, and layer 3 uses IP addresses for communication. Now in the next couple of videos we'll discuss in a bit more detail about IP addressing and MAC addresses, but for now we're going to have a high level view of what the different types of messaging like Unicast, Multicast, and Broadcast allow us to do. Now, Unicast can be thought of as something very simple. Essentially, Unicast is a one-to-one communication. So if we just draw a switch, remember this is the icon for switch, and off the back of this switch we have, let's say, a PC and another PC, and let's say another one. And PC1 wants to speak to PC3, and PC1 is able to, let's say, communicate with that PC directly without involving PC2. This is considered Unicast because it's a one-to-one communication. When we think about the others, which is Multicast and Broadcast, this is where it gets a little bit more complicated. So, Multicast essentially means one to many. Now, Multicast example would be, let's say we have another PC down here and we're running some sort of multicast technology or multicast protocol, which is way beyond the scope of the CCNA and the CCNA, but I want to use it for sort of a theory. Let's say, for example, PC1 is streaming some sort of video. What can happen is PC3 and 4 will be set up to listen to that video, so the switch would know to send that communication to 3 and 4, but not to 2. This is a multicast communication. So it's not to everyone, but it is to more than one. So another example of this is, let's say we have our routers, and our routers connect into a switch, and at the back of the switch we also have two PCs. Let's put another router up here. Now let's say these routers are running RIP, which is the Routing Information Protocol, and we're going to be running version 2, because version 2 takes use of multicast, whereas version 1 uses broadcast. So RIP responsibility of RIP, we've not discussed this in detail yet, but RIP essentially is to advertise subnets to one another. So off the back of this router, let's say we have 192.168.0.0/24. The back of this router, we have 172.16.0.0/24, and on the back of this router, we have 10.0.0.0/24. And all these routers are on the same subnet. Let's say he's a .1, he's .2, .3, and even these PCs are on the same subnet. Now, RIP, the responsibility of RIP is to advertise the routes or advertise prefixes to one another. So for example, let's say this guy here, he's aware of the 192.168.0.0/24, but this particular router doesn't know how to get to 192.168.0.0/24. So RIP can be used to advertise this router as a gateway for 192.168.0.0. So if this particular router had a packet destined for that destination, it will know, I know how to get to 192.168. To get there, go to .3, because .3 knows how to get there. But that communication, if you like, happens via Multicast. And the way that works is every router on the link, every so many seconds, will actually dump, if you like, or send a list of all of the routes that particular router is aware of to a particular multicast address. And that multicast address is 224.0.0.9. And that's a layer 3 IP address. And when it comes out onto the wire, this router and this router will be listening for packets destined to this IP. And when those packets come in, they will actually be, the information will be able to be interpreted and learned. These PCs down here will not be listening for the 224.0.0.9. Therefore, the traffic will not be sent to the actual PCs themselves. So what we have again is multicast, where even though they're all on the same segment and they're all on the same subnet, only 3 of the devices are communicating through multicast communication. Now, if we were not running 2, and instead we were running 1 uses broadcast, which means instead of the 224.0.0.9 address, it's actually 255.255.255.255. This means everyone. So when this router now sends out its routing update to say, hey everyone, these are the subnets that I'm aware of, it will go to every single host. This PC would have to accept that packet in, process that packet, realize it's not for the PC, and drop it. The downside being a few reasons. 1, we're using utilization of the NIC card of this PC, processing packets that are not relevant. 2, it's a big security concern. If there was a rogue PC plugged into this particular network and running something like Wireshark, he or she would be able to capture traffic or essentially routing updates from your router and then know what particular routes exist on your network. So the differences between unicast, multicast and broadcast. Unicast is a one-to-one communication. Multicast is a one-to-many communication, and a broadcast is everyone. Later on, when we discuss things like ARP, the address resolution protocol, you'll see how the ARP process uses broadcast to communicate with everyone initially, but once it learns where the hosts live on the network, it then uses unicast to communicate with them. And when we come to ARP, this is where your foundation of unicast and broadcast, etc., will actually come to light. And when we get into things like routing protocols, this is where things like multicast will come together for you. A broadcast domain is how far a broadcast message, whether that's layer 2 or layer 3, can travel within a particular network. So, first of all, everyone inside the particular broadcast domain will see the frame. The traffic can be sent at layer 2 to the all Fs, or at layer 3 to the 255, 255, 255, 255. And another key part about broadcast domains is routers stop the broadcast message. Now, to give you a good example of a broadcast message, let's say we had a DHCP server here. So the Dynamic Host Configuration Protocol. And for those who don't know what DHCP is, it's a protocol that allows you to hand out IP addresses to PCs on the network dynamically. Let's say over here we have a PC that was just plugged into the network. And of course, when it's plugged into the network and we want to utilize DHCP, the PC itself will have a null IP address or a 0000 IP address. And in order to obtain a IP address, it's going to send a broadcast message to everyone inside the broadcast domain. So it will start off by sending a message to the OR 255 host or to the 255 destination. So the message will go out destined for the 255, 255, 255, 255. It will be received in on the switch port. The switch will look at the destination, and in turn it will look at the frame of which the DHCP message was crafted with, and inside that frame it will actually have a layer 2 of all Fs, and inside that packet it will have a layer 3 of all 255s. But because we're using layer 2 switching as our example here, we know that layer 2 is where Ethernet sits, so the switch will see the all Fs inside that frame. It will see the all Fs, and in turn it will say this is a broadcast message, and a switch will continue to send that broadcast message to its directly connected devices. When these switches receive the message, they too will send it to all of their connected devices, as well with all the upstream, i.e. towards the routers and towards where we ideally want the message to go, the DHCP server. Now, because by default all PCs and clients are listening to these broadcast messages, every single device, let's say we had about 40 devices connected to these 3 switches, will all receive, process and drop that information. So not only does it consume bandwidth by sending that message everywhere, but it also consumes the utilization of the host. However, let's say our DHCP request has actually reached the destination. The destination will listen for that frame on the correct layer 4 port, which I believe is 67, and send a response, a Unicast response, back to the PC itself. So that's an example of a broadcast, or that's an example of why we would need broadcast traffic. Now, how far does that traffic actually travel? Again, the distance of it is called the broadcast domain. Now, a key bit here is routers will stop the broadcast message. Meaning, let's say we had our DHCP server connected to this particular router port over here. When our PC fires up and sends out that DHCP request and it gets flooded to all of the devices, this particular router here will stop that message and no longer allow these broadcast messages to travel beyond that particular domain. So because of that, what we can say is, looking at this picture, is there are actually a few broadcast domains. There's a broadcast domain between these 2 devices. There's a broadcast domain between these 2 devices and any device connected off the back of these switches. And there's a broadcast domain here. So what's a broadcast? A broadcast is a message sent to everyone inside the broadcast domain. Protocols like DHCP and other protocols like ARP, the Address Resolution Protocol, utilizes the broadcast element to reach everyone on the wire and hopefully get a response from the correct party. Routers stop broadcast messages, so they are not flooded to everywhere. And the downside to broadcast messages is everyone on the wire receives it. Everyone on the wire has to process the information, whether it's for them or not, and in turn drop that information if it's not for them. So ideally, what we want to do is a few things. First of all, we want to lower the amount of broadcast information we have on our networks by using things like Unicast and, where applicable, Multicast. And what we also want to do is decrease the size of the broadcast domain. And we can do that by introducing routers, or, as we'll see a little later, we can utilize things like VLANs to help us split up the broadcast domain. Okay, so away from broadcast domain and talking about collision domains. A collision domain is a shared medium. Essentially, who shares my link, if anyone. So an example of this, let's go back again to our bus topology. We said that there was a long cable through the office and each device would connect into this cable. And when one person sends traffic onto the wire, the traffic would be sent to everyone, whether it's destined for them or not. Very similar to kind of a broadcast method like we talked about previously. But the problem here is only one device can communicate at a given time. So if we had 100 PCs connecting on this particular wire, obviously there'd be problems with the network because only one of those devices can communicate at one given time. And then the Ethernet and an extension of Ethernet, which allows us to accommodate for this, is CSMA CD, which we'll get onto in a moment. So a few things to keep in mind with collision domains. A hub is a single collision domain, but bridges and switches, each port is classed as a collision domain. Same to be true with routers. Let's look at this quick diagram down the bottom here. We can see we have a couple of routers, a couple of switches, and we have a hub over here. Now let's say on this hub, we had 4 devices on the back of it. All these devices would be considered in the same collision domain. Because this here, all these devices on this hub would be as if they were all connected to the same physical cable of a switch. Because they're all in the same collision domain. And the reason for that is because when data is sent into the hub blindly sends it out all the ports, because a hub is essentially what we call a repeater. So all of these might as well be on the same physical cable, but physically they're not, logically they are. A switch is a little different. Each port on a switch is its own collision domain. So for example, this person that's connected to the wire and this person that's connected to the wire, well, because they're on 2 different ports on the switch, both of them can transmit at the same time because the switch uses buffers and its CAM table to essentially store and forward the information to the correct destination without having to have repeat it out all of its ports. So we consider every port on a switch its own collision domain. Same to be true with the routers. Not only do routers break up the broadcast, but they also offer a collision domain of the port. Okay, so let's move on to the carrier sense multi-access with collision detection. So the CS, what does it mean? It means carrier sense. There's a PC or a host and it has to perform what we call carrier sense to determine if anyone else is talking on the wire in order to be able to send its traffic. So let's say we have a hub, and off the back of the hub we have multiple devices. Each device will perform the carrier sense to determine if the wire is free before it sends traffic. How does it determine whether the wire is free? Well, like anything, this is copper cabling and it uses electrical signals to send data. So there'll be a set level of voltage that the device itself will be listening for. and if that voltage is higher than normal, then someone must be sending traffic. So it listens, and if that voltage is at the level it would expect, then it will be happy to determine that no one else is sending traffic, and therefore it can start to send that traffic. The MA in the CSMA CD stands for multiple access. We know Ethernet is called a multiple access medium because back in the original design with the bus topology, everyone connected to the same coax cable and everyone received the messages, whether it was destined for them or not, from everybody else. Same is true when it connects to a hub. Everyone is in that same collision domain. We know nowadays with switches that every device connects to a switch is in its own collision domain, so we don't have problems. But Ethernet is still considered multiple access because the opposite of multiple access is point to point. And we know that if you plug a PC into a switch, it doesn't connect directly to another PC, it can connect to multiple other PCs, even though they're all on different collision domains. Another technology is NBMA, which is non-broadcast multiple access, which are technologies like frame relay, where it doesn't support broadcast messages, but it's also not a point-to-point. It has multiple devices or hosts that can be reachable out of a single link. Lastly is collision detection. So the CD stands for collision detection. So while a device is actually transmitting data onto the wire, it's possible that another host may also start transmitting. And the reason for that is because both of them were in the carrier sense phase at the same time. So they both looked at the wire, seen no one was sending, and started to send data because they both thought the wire was clear. If a collision occurs, and the way the sending device, let's say this person, knows that there's a collision is because all of a sudden the traffic they're sending, they start to receive a lot of electrical bounce back, and because of that they make an assumption that someone else must be sending at the same time, and the host will send what's called a jam signal onto the wire, and everyone in the collision domain, so again everyone connected to that coax cable or everyone connected to that hub, will go into a random back off, meaning every PC will essentially stop communicating and step off and wait for a set period of time. That's a random value. And when that random value is up, they would then go back and sense the carrier. And it's clear now why having lots of devices in the collision domain could cause a big problem, because if your Ethernet segment is too busy, more and more collisions will occur, and the back-off timer will get bigger each time it occurs. So let's say the back-off timer was 100 milliseconds, and then it carrier sensed, started to send the traffic again, and then it detected another collision, it will increase it to 200 milliseconds, as an example. Ethernet will try to put data onto the wire around 16 times, and then it will eventually just give up and not send that traffic or attempt to send that traffic. Now, as I said, CSMA CD is a method used by Ethernet back when it was a multiple access technology, in the sense of, they all shared the same medium. It's still considered a multi-access technology because we know Ethernet, you can have multiple devices inside the same broadcast domain, therefore it's still multiple access, but we don't share the same medium because each device has its own collision domain because they plug into the switch. So CSMA CD isn't necessarily something you turn off. In fact, I don't think you can turn it off, but it's something that I don't know whether it actually runs on the NIC or not, but if it does run, it's certainly not used as much because very rarely are there collisions because there's no one else on that shared medium. And because there's no one else on that shared medium, we have the ability to send and receive simultaneously, which is referred to as full duplex. Okay, so that's all we've got time for in this lesson. Just a quick review of what we learned. We talked about broadcast domains. We said that a broadcast domain determines how far a broadcast message can be sent within a network. We said that routers help break up the broadcast domain, which is important because if our broadcast domains get too big, we can end up with something called a broadcast storm, which is where there's too much information on the wire, or it's where things like looping occurs, where we don't correctly configure what we refer to as the spanning tree protocol, which we'll get into a little later. After understanding the broadcast domains and why we might actually send broadcast messages onto the wire or into the network, we then had a look at collision domains. We said that every port on a switch is a single collision domain. So every device has their own collision domains, which means they can send and receive simultaneously. And because of that, we get this option to run full duplex. Whereas if we were to use a hub, every device on a hub is in the same collision domain, and because of that, they're all half duplex, as in they can only send or receive, and they can only send and receive if no one else is sending and receiving, because they've got to utilize that CSMA CD, which is the carrier sense multiple access with collision detection, which is the method that Ethernet uses to sense if someone else is sending the data, and if they're not sending the data, to send the data themselves, and if a collision were to occur, to be able to detect that collision and let everyone else aware that there's been a collision and that we all need to react to it. I hope that's been informative, and I'd like to thank you for viewing, and if it has been, please do like and subscribe.